Hi and welcome to What Circuit. I'm David, Charles doing the filming today, and today we're up at Lancashire Cricket Club and we're at the Motiv8 Forums once again, talk to some really interesting companies. Harvey's who actually runs it is going to tell us a bit about it.
Yeah, thank you, David. We run technical forums for engineers around the UK here in Manchester today at Emirates The Point and also in Cambridge and in Oxford. They're free events for engineers, design, technical engineers, electronics engineers to attend.
So we're here with Ian from EBV Elektronik, who's going to talk to us about some of the devices from Analog Devices, looking at low power RF Internet of Things.
Okay, yes, thank you. Yes, really what we're demonstrating here is what the Internet of Things means in a practical reality. So it's a buzzword that's rather overused, and without, I think, people understanding what it is. And to me, what the Internet of Things means is a sensor that needs to send information back through the cloud to an application. And what we're focusing on is how do we get that information from the sensor itself back into the cloud. Mm-hmm. And what this is using a transceiver product from Analog Devices, which works in the sub 1 gig band. This particular one in Europe is at 868 megahertz, and this is a license-free band allowed to be used for short-range devices and low-power devices. So on this device we can have a simple sensor. Mm-hmm. I've got one with an accelerometer, I've got another one with a temperature sensor on it, and all it's doing is sending temperature or positional information back via the RF link to the edge gateway, which is here. So this is running off a little coin cell, a CR2032 coin cell battery. It's operating with an output power of around about 0 dBm, that's about 1 milliwatt, that's exactly 1 milliwatt. And it's sending very, very low data rate, simple data information, in this case about the temperature, which is displayed here, so it's 20.4 degrees in here. Now, this can be used within this kind of an environment. The range is not too important, but the advantage of the sub 1 gig frequencies is you can get significantly longer ranges, which might be useful for smart metering applications. And being able to use very low power and being able to operate off a coin cell is all very well, but it's no good if you have to change the battery every few days. So what we need is circuitry, a CMOS very low power design that will let the circuit or let the sensor run for maybe a year or two before you have to change the battery. And that's the practical reality of what the Internet of Things means when we're talking about a sensor that needs to connect back into the Internet.
So you're really focusing on low data rate, simple message commands that you might have a bit of latency, it doesn't matter.
Yes, latency doesn't matter, it's low data rate. You might be transmitting some information once a minute, once an hour, maybe once a day if it's the water level in a reservoir. You might you might only need to care about it once a day. There's a little bit of data overhead, obviously, for the protocol and the signaling, but all we're really talking about is sending a few bytes of data every so often. So yes, it's very low data rate. You certainly wouldn't be video streaming with it, nor would you be sending firmware upgrades, for example, which low power RF and the sub 1 gig band is not really designed to do that. We have the much higher data rate protocols such as wireless LAN, which we all know in our homes, which you can do that, but don't try and run it off a coin cell.
So you say about your solution, does your solution just capture, does it just cover transmitting the wireless data and receiving it, or does it go more than that?
What we're focused on here is the RF link in the Internet of Things. I mean, if you take the entire structure, you've got a physical layer, which is based on 802.15.4. This is the physical layer. Then you will have the MAC layer and the protocol stack above that, and then finally you're into an internet gateway and into the cloud and into the application. Yeah. We're just focused on that very last wireless hop out to the edge of the network, if you like, that final node on the edge of the network.
Yeah. And so can you just connect a sensor straight to your IC?
There are a lot of different solutions. The simplest level, a transceiver IC just transmits and receives data packets, and what you send to it is whatever you want. The Analog Devices, this particular device has a Cortex M3 in it, so there's with that is the transceiver on a single chip, so you can run the protocol stack within on the processor, but there's also sufficient memory space left to run your application on. So how you write the application and what you want to send to it is up to the clever guys that are going to make the Internet of Things big.
Excellent. So you've got a industry standard processor built in there. You've supplied some code for your side. You just add on to that, and you just create your own custom application on top of there.
Yes.
So in terms of power supplies, you just run this straight off a lithium battery?
It's running purely off a CR 2032 coin cell.
So no power regulation needed, no buck boost, nothing like that?
It needs to be CE certified, of course. It's at the end of the day, it's a radio transmitter, so that is defined by ETSI. So there is a specification that it has to meet, it has to be compliant to, and any product placed on the European market has to be CE certified. That's true of anything, not just electronics or radio.
Yes. So I noticed you've got a couple of different aerials with your solution here, so you've got some different reference designs?
Yes, this is just a demonstration, but one of the key things with sub 1 gigahertz is, well, what sort of range can you get? We're used to Wi-Fi in our house, maybe giving us a few tens of meter range. Bluetooth low energy is good for that personal area network at a few meters. What we're really trying to do at sub 1 gig, we're really looking for longer ranges than that. And then there has to be a trade-off. If you want to go for a longer range, you can transmit with higher power, but that has an impact on the battery life, on the power consumption. You can reduce the data rate, that helps. You can do things with the antenna. This sensor just has a very, very simple, very small chip antenna, not very efficient, but very, very small. It can be put into a very small module.
Right.
But something like the quarter wave whip, which is on the edge gateway, the edge router here, is obviously going to be a lot more effective. And we have software which will let you simulate the kind of link distance that you're going to get. We can do a link budget calculation from the transmitter. We may have a power amplifier. Parts of the spectrum allow a higher output power up to about half a watt. So that is possible at the expense of power consumption. There's obviously path loss on the radio link itself, and then on the receive side you might have a low noise amplifier.
Can you show us through the software? That was quite interesting.
Yes, it's this is an ADI SRD, and it's just a short-range device simulator for the software. So what we can do is we can input the basic parameters. It makes it simple because you can pull up the integrated circuit directly within the software. So it will take all the integrated circuit specifications and use them. But then we can start to simulate, okay, well, what sort of antenna gain have we got? If we're using a quarter wave whip here, it's got about a 0 dB gain. A chip antenna such as this is actually probably going to have less than a 0 dB gain. It's not really very efficient. And depending on how it's mounted, it might have some directivity as well, which may or may not be desirable, but it's going to have it anyway. So we can put antenna gain or loss in there and simulate it. The other thing that's going to have a big impact on the range is the data rate and the channel bandwidth. If we want a very high channel bandwidth and sending lots of data through it, it's going to reduce the range. If you narrow the channel bandwidth and you slow down the data rate, smaller channel, less noise, longer range. So we can simulate that. So in this example, I'm showing a link pretty similar to what we've got here, and it's coming up with a range of about 800, well, a little bit less than a kilometre, just shy of 900 metres.
Excellent.
That's in perfect conditions. Look out to the window, there's some trees, there's some buildings. If you have that in the way, that's going to reduce the range. So really, when you're calculating the range, you really need to assume a fade margin of some dBs. Otherwise, the link's only going to work downhill with a tailwind, which you wouldn't do as a designer, obviously.
But speaking as an embedded engineer, it's fantastic just to have the tools to get that initial idea of roughly what you're looking at.
It's simple, and it just gives you a basic idea of what can I expect to get in terms of range, in terms of data rate, and in terms of battery life of a simple sensor network, and what are the compromises I need to make if I have to optimize one of those. I might have a node right out at the edge of the network where range is all important. If I can plug it into a power supply, I'm not too worried about power consumption. I might have a sensor that's really hard to get at, maybe a water meter or something, where I can put a reasonable sized battery in but I don't want to ever go and replace that again. I want it to work for 20 years. But you can do that. You can make those types of calculations and adjust the network to compensate for that. And that's really the purpose of the tool.
And you're saying about adjusting channel bandwidth and those kind of trade-offs. So you can actually do that all in the processor, and so you can actually change.
Yes, the RF physical layer follows exactly the 802.15.4 specification. Right. That has a number of different modulation schemes, channel bandwidths, data rates. So that is all contained within the 15.4 specification, and you can use any one of those standards within the physical layer to optimize the link for whatever your requirements might be.
That's it. So as an engineer using it, you can just literally pick the appropriate modulation scheme, which is still going to be compliant. You've done that in.
Yes. So what we can do here is we can simulate what effect that modulation scheme will have on the data rate, on the bandwidth, on the link range, on the power consumption of the device.
Excellent. So your ARM processor must be very tightly coupled to the hardware to get that level of control, presumably.
Yes. I mean, that's contained within the protocol stack. There is Analog Devices has its own protocol stack, which is royalty free. It's available with demo sensor, and it manages that communication back and forth. So it's fairly simple to set up.
Excellent. And talking about sort of moving to battery life and that kind of thing, you said you have some calculators showing battery life as well, so you get an idea.
Yes, we can. Again, I took this as a sort of a fairly typical link range. If I move on to a different tab here, I can look at the power consumption of the device. The power consumption is again can be a bit of a spectatorship game. What's important? Is it the hibernate current? Is it the transmit current? Is it the sleep current? Well, the reality is it's all of them, and what matters is the profile of how you're using the device. So I've just picked an example here where we would have a hibernate time where literally it's just switched right off, and the power consumption, the current consumption is down in the nanoamps. So it's really not much above the leakage level of the battery. But then you need to wake up, you need to wake the device up, so it's going to come out of hibernate. It'll be in a sort of a low power idle mode. You might want to check the channel before you transmit on it. So then the receiver's going to come up, is this channel free? Remember, these are license free bands. Anyone and everyone can use them, so you can't assume you've got a frequency available for yourself. And then you're going to go into the transmit cycle. Maybe you want to receive an acknowledgement back from a routing node in a mesh, or back to the edge gateway. You might want you want an acknowledgement. So you've got a transmit cycle when you're sending the data. You've got a receive cycle, and then you've got a hibernate cycle. And the profile of what that hibernate, sleep, receive, transmit is really what's going to define your battery life. And again, we can simulate it here. So what this is showing on the example I've taken is that we've got a battery life of nearly 20 years. Now that's assumed that I've got a 1 amp hour battery in there. I'm not sure what the capacity of a CR2032 is, but it's not it's not 1 amp hour. It's 100 milliamp hour, 150 milliamp hour, something like that. So we're probably looking at an order of magnitude less battery life, say 1 to 2 years, something like that. But for many applications, that's perfectly acceptable.
Absolutely. And interesting, when you get into this sort of area, you have the trade-offs. Is it worth transmitting your data quicker and then getting it back into hibernate mode quicker? And this calculator presumably really allows you to get into those trade-offs quickly.
I mean, do you use a wider channel and faster data rate and therefore have a much shorter transmit time, or do you use a very narrow channel with a longer data rate, but then recognizing that you're going to have to transmit for longer? There are a lot of trade-offs. You need to model it and simulate it to get an idea of what you need for your specific link.
Excellent, that's a really nice solution. And I've got all the tools around to support it. You've got the reference designs, you've got the antennas, everything. That's really interesting. Ian, thanks for your time.
Okay.